right. So our next talk is by Yaozhu from University of Hong Kong. So take it away.
Yeah. Thank you everyone for coming. First let me adjust the microphone a bit. Oh, that's okay. Yeah. Welcome to my talk. Today I want to talk about imperative computational programming. And this is a joint work with Wenjia and Bruno. First, you may notice this. We have a very long subtitle, and I want to divide it into several keywords. Yeah. Then we start with imperative computational programming, ICP for short. And computational programming is a programming paradigm we recently proposed to mainly solve the expression problem. If you know expression problem, if you don't know, that does not matter, because it's basically a dilemma of extending two dimensions. One is the expression, one is the operations over these expressions. For example, if we want to model a mini language, for example, we have variables, assignments, sequential conversation, then we go for the x-axis, and we want to extend more, like we want while loop, and do while loops as two variants. And also, on this axis, we want to extend, we want to implement more operations on these data types, like we want to print, we want to construct a control flow graph on it. In CP, computational programming, we have a very modular solution to it, and we can have 4 modular traits that each implements every point in this coordination system. And if we take a closer look at, I want to mention that we also support modular dependencies, like we can depend on print on the red top corner, that our graph, the new node function, also have a self.print to have the modular dependencies. In some similar approaches like final tagless, it's very difficult to implement that. But we want to have a closer look at this function because we have imperative things like references. For example, the goal is to build a control flow graph like this one. And sorry, I pressed the wrong button. And this one has a data type graph that's a point, like the pair of nodes, pair of references of nodes, like 2 pointers. One points to source, one points to sink node, and we have made a lot of use of references like assignments, creation of references, and dereferences here. The ban is for dereferences. The adjacency array is like a mutable field here. And here comes the intersection types. To make use of the modular traits, we may want to merge them together, like here in the merged, we have all the constructors. Then we can build a expression making use all of these constructors, and every constructor have print and graph together. The operations can be used from this merged. And here the comma is a merge operator, and is virtualized below. And on the type system, on the type level, we have intersection types serving as the interface here. And you may wonder, what's the problem with intersections here if we want to add in mutable references? Now we dive into the type theory below our imperative computational programming. Here, an intersection type basically means if your expression E has type A, and E also has type B, then E has the intersection type of A and B. That's a basic idea. And simple example is positive numbers and natural numbers. You can find there is a subtyping relation between them, and you can easily derive that 1 is both a natural number and a positive number, so it has type net and post. That's the typical introduction rule for typing. And for subtyping, we have 3 rules. The first 2 handles the case that intersection types occur on the left-hand side. For example, if you have an expression E has an intersection type, you can use it as if it just has net or has post. The third rule, you can use it to permute the components inside the intersection type. For example, net and post is equivalent to post and net. That's very intuitive. You can derive it using both all the 3 rules. And for references, we have 3 primitive operations. The first one is to create a reference. The second one is to do assignments, and the empty parenthesis is the unit type. It means you can discard it. And the third one is the dereferences. To give you an impression on these type systems, I have a program that creates ref1 to have a reference cell that stores that 1, and we assign 0 into it. And at last, we want to dereference it and want to use it as a positive number. You may have noticed it's wrong. And let's see how can our type system detect it. Here, you can find ref1 definitely have ref post, but for assignments, you cannot use ref post as ref net because the subtyping for references is invariant. So, yeah, on the second line, there should be a type error. And when intersection type comes, the program becomes a bit complicated, and we can bypass the type checking to make it type unsound. Again, let's go through it from the first hand. So from the first line, we have the reference type. We can type ref1 with the reference type refnet and refpost. This intersection type with both reference types, and initially x points to 1. So far, so good. But if you want to do assignments, you find it works because you can take the left half of that intersection type here, and you can assign 0 into that reference cell. And oops, at the last line, you want to use 0 as a positive number, but it's not. So you may encounter a runtime error. In other words, it's type unsound. Actually, it's a well-known problem, and the solution is proposed by Davies and Pfenning that they impose a value restriction. If you are familiar with OOPSLA, you may have seen a similar version of that value restriction, but this time is to make sure that the reference does not introduce type unsoundness. Here, we can see ref1 is not a value, so you cannot type a non-value with intersection type here. So it's forbidden. Now the system back to type sound, but distributive type subtyping breaks type soundness again. Here, we have instantly invoked function, and with very long derivation. Trust me, that if you don't trust me, you can work it out, and you bypass the type, the value restriction, and get this expression with intersection type again, and is back to type unsound. So that's a very complicated problem in the literature, and we don't find a very good solution in the literature. So how how do we handle that? The bidirectional typing come to rescue. And before we have the comma in the judgment, it's called type assignment system. And it can actually be divided to 2 separate judgments, and this system become more algorithmic because for type inference, it has algorithmic meaning that it can be inferred to type A. And for type checking, you have 2 known things. One is expression, one is the type, and you checked the expression against the type. Usually, we also have a subsumption rule that to bridge, to fill the bridge between the 2 typing modes. Back to the very simple example on numbers, we can see that now 1 is supposed to infer typos, and that is the most precise type of 1. And in most bidirectional typing systems, 1 expression can only infer 1 type, because that's the more deterministic way to do that. And if you want net, then you can check net against, you can check 1 against type net, and the subsumption rule will help you do that. In short, 1 can be inferred to be typos and also checked against that, but net can only be checked against net, but not to inferred to have type net. And here, if we want to apply bidirectional typing to references, Davies and Pfenning proposed a solution, but does not work as we already mentioned, because this system is almost equivalent to their type assignment system. We have a different formalization using bidirectional typing on the 3rd line. And maybe to your surprise, the most important rule is the reference rule, the tref. And the difference is that we don't check, we use the inference mode here. And you can ignore the other 2 rules here and only focus on tref. You can see ref1 can still be we can still infer ref1 to have type refpos and also check it against refpos, but now it cannot be inferred to be type refnet, nor it can be checked against that type. This solution is very simple, but it can solve the previous type assigned case here, because no matter the reference 1 or the instantly invoked function, they cannot have type refnet, because to be honest, we have the most precise type for all references, so that less precise type cannot be used here. So the type soundness is back again. You may wonder, if you want to have refnet, how can we do it? That's very easy. We can have a type annotation. And in a bidirectional typing system, it will invoke the checking mode, and you can naturally have refn, colon refnet, and use it as refnet below. But it cannot have refpos anymore. Otherwise, the type unsoundness will come back again. To conclude, our advantages over Davies and Pfenning solution is, first, our intersection introduction is standard. We don't have value restriction. And distributive subtyping is supported. Why distributivity matters? Because we have shown in the very beginning. But first, logical implication is left distributive over conjunction. So that's a direct corresponding between the logical system and our lambda calculus. And more importantly, distributivity of traits is encoded as functions of records. And it enables nested trait composition we showed before, and that's the solution to the expression problem. We cannot drop distributivity here for our ICP. Last thing, we have more in our paper, more introduction, complete code, and we have code formalization for both calculi. One is based on the calculi by Davies and Pfenning, but employing our solution based on bidirectional typing. And a more complicated calculus is the foundation for our imperative computational programming. And both proofs are mechanized using calc. Oh, sorry. That's all for my talk. Feel free to ask me questions. And also, my co-author Wenjia is here. Yeah. Thank you very much.
Thank you. Questions? All right. So, I mean, it seems like a really simple innovation in design, and so I think that's really cool. So, can you say a little bit about how did you end up with it, and maybe why it wasn't sort of in the original, if you will?
Yeah. Actually, we don't start with the problem found by Davies and Pfenning. Actually, we start with. Let me just hold the microphone. You want to? I will step in first. And we actually start with our design of computational programming, and it's quite natural that we just since computational programming also use bidirectional typing for other reasons. For example, we have imperative, imperative polymorphism, and we have more complicated systems. We naturally have bidirectional typing, and we find infer can conclude a type sound calculus, and we find it's a long-standing problem in the literature. So we start from our own language and go back to the old problem and solve it altogether. That's the story of our design. Maybe you can add more things.
Yeah, it's some kind like that. At first we are not aiming to solve this question. It's like we solve it accidentally. Yeah.
Yes.
So at first we are going to like add multiple references to our own language in our group called CP. Yeah, you can use that language as well. So and when we add the multiple references and we see that their intersection type and multiple references and their findings work, and we see their restriction is quite like to overhead. So we think another approach and accidentally it solved the problem in their paper as well. Yeah.
Very cool. Other questions? All right, I'll continue then. I mean, it seems like such a simple solution. So is it actually more expressive? Do you lose something? Is there a trade-off in the, using the value restriction versus your system, or is it just better?
I think the most important thing is that one expression can only has one type. It's not true in some more complicated typing system that you may do backtracking. You may want to have expression have multiple types, and only one of them works in the later stages, and you want to backtrack and do a lot of things. That's the case in another work in our group for type inference. Yeah, I think that's the most important restriction we have.
So one more.
Did you also compare or consider versions of the reference type, which has two type parameters, where it is covariant in one parameter and contravariant in the other?
Yeah, you can.
For references, we are also invariant. Yeah, we haven't considered the coinvariant. Yeah. So now for reference type, they are invariant. So maybe this is also one future direction that you can explore something. As I know, there's something like thick type, and also I'm not sure, but they can make it covariant. Yeah. I think that can be one future direction.
Let's thank the speaker.
Thank you.